Okay, so we're going to take antiderivatives a step further. And do you remember how I told you that antiderivatives go hand in hand with integrals? So what we're going to look at today is how to evaluate a definite integral. So let's talk about a little bit of theory first. So we know so far that you can find antiderivatives and that we use this symbol. And this symbol is for an integral, and we use the word integrate, and the process is called integration. Okay, so that's all fun. And this thing has a purpose, and here's what the purpose is. Let's say we have a curve, okay? Here's our curve. Here's just a nice parabola. The next level of calculus is going to focus on the area that's happening underneath a curve. Like if you tried to figure out how much area was underneath this curve, it would be really difficult, right? Like if I asked you for the area in a square, you would multiply length times width and it would be easy. But if you come over here, this is not so easy because like you've got like this little thing, and then you've got maybe you could draw like another rectangle here and then another rectangle here, but it's not really like totally accurate, right? So it gets really tricky to figure out the area under a square or a curve. So the area under a curve is really our goal. This is our objective. This is what we are trying to find, and to do that we use integrals. Okay? Now, as you can kind of see, there are some methods you could use to estimate, right? You could do this whole like rectangle thing, and you could potentially find the area of all these rectangles and add them together. But you can see that even that, like I'm missing little parts, right? Like my rectangles aren't hitting that curve perfectly. So it becomes a thing. It's very difficult. So this is called a rectangle approximation method. Method, which is also known as RAM. But it's not that great. So we're going to instead do something called finding the definite integral, okay? And that means we're going to use an antiderivative to find area. All right, we're going to use the antiderivative. Okay, so what we should note is that if we look at this curve goes on forever. So that means the area under it is going to forever be increasing, right? So the key to our success here is going to be to look only in a specific spot. So we're going to look only, let's say, from x equals 1 maybe to 4. Wow, this is getting really messy really quick. Okay, so we're going to only look in a specific place when we use definite integrals. We're only going to look in specific places. Okay, let's rewrite this so it makes a little more sense. So let's say we've got a function f of x equals x squared. Here's our graph. Here's what the parabola looks like. Okay, not exactly like that, but close enough. Let's say I would like to know about the area under the curve of x squared. A lot of times we put brackets around it because remember we're going to write dx after it. But I only want to know what's happening from 1 to 4. Okay? So I only want to know what's happening under this curve, what the area under this curve is from 1 to 4. We need that information in our function. So we're going to put numbers at the bottom of our integral sign and the top. So we're going to put 1 to 4. And that's telling us that we only want to go from x equals 1 to x equals 4. We're only interested in that area. these numbers have a name. This is called your lower limit. And this is called, anybody want to guess? Your upper limit. Your upper limit. Okay, so your lower limit in your lower limit and your upper limit. And if you take the integral, if you integrate with an antiderivative, x squared, you will find the exact area under this. So when we find the definite integral, we're going to get an actual value. Like, remember, when we found an antiderivative, we just had a formula, right? We had variables, we had an x. But today we're going to get an actual number. Okay, so what is the antiderivative of x squared? Well, the antiderivative of x squared, remember, is x cubed over 3. Now, we are going to not worry about the plus c part today. It's not going to impact what we're doing today. So that means to find the integral, we are going to take f of 4. Now, capital F means antiderivative. Okay, capital F means antiderivative. We're going to take the antiderivative of the upper limit, and we're going to subtract from it the antiderivative of the lower limit. Okay? So what that means is we are going to take, let me make this a little bit smaller. We are going to take our antiderivative, which remember is x cubed over 3, and we're going to substitute in our upper limit, and then we're going to substitute in our lower limit, and we're going to subtract them. So we're going to say x cubed, we're going to say x cubed when x is 4. So 4 cubed over 3 minus 1 cubed over 3, right? So what I did there was I took my antiderivative and I plugged into that my upper limit as 4 and my lower limit of 1, and I'm going to subtract them. Okay, so what is 4 cubed divided by 3? 4 cubed divided by 3 is 21.3. So that's 21.3 minus 1 cubed is 3 divided by 3 is 1. So 20.3. That represents the area underneath this curve in between 1 and 4. Okay? That's how you find a definite integral. Let's try another one. What if we want you to evaluate or find the definite integral of x squared plus x minus 2 from 3 to 4? Okay, so the first thing we're going to do is take our antiderivative. So what's the antiderivative of this? The antiderivative of this is, let's see, x squared. We're going to add 1 to the exponent and divide by. So x cubed over 3 plus x. So I'm going to add 1 to my exponent. So I'm going to have x squared divided by 2 minus 2x. So this is my antiderivative, f equals. I am going to take this and I'm going to substitute in the 4, my upper limit, and then I'm going to subtract from it the lower limit. So remember, I'm going to take f of 4 and subtract f of 3. All right? So here we go. We're going to say, I'm going to work this over here. I'm going to say 4 cubed divided by 3 plus 4 squared divided by 2 minus 2 times 4. Okay? That's going to be one big piece. From that, I'm going to subtract. I'm going to use another giant bracket. And this time I'm going to substitute in 3, my lower limit. I'm going to substitute 3 in for all my x's. So that's going to give me 3 cubed divided by 3 plus 3 squared divided by 2 minus 2 times 3. Giant bracket. Okay, get out your calculator, crunch those numbers. I'll wait. Okay, so let's see, 21.3 plus 4 squared is 16 divided by 2 is 8 minus 8. Okay, so 21.3. Over here, we got, okay, so 9, 3 squared is 9, plus 4.5, minus 6, plus 4.5 is 7.5. Okay, so we had 21.3 minus 7.5, which gives us 13.8. And that is the definite integral. Okay, so recap. You take the integration sign, you look at the lower limit, which is written on the bottom, let's say 2, to the upper limit, which is written on the top, 5. You have a function. Let's say your function is 2x squared plus 4x dx. You find the antiderivative. You plug your upper and lower limit in, and you subtract the lower from the upper. So here our antiderivative would be 2/3 x cubed plus 4 over 2x squared. We would take that and we would plug in f of 5 and subtract f of 2. That will give us the definite integral, right? And that represents the area underneath the curve between 2 and 5. That's it, you're done.